We'll move on to our second speaker, who is Sebastian Mizera, who's going to talk about the sandwich model.
Okay, well, first of all, let me thank the organizers for inviting me to give a talk today. We've already heard a great talk just now, and I'm looking forward to the talks later today and tomorrow. So today I wanted to tell you about something that we call the sandwich model, which is the set of ideas that we've been thinking about with my fantastic collaborators at the Institute for Advanced Study, Lawrence Eberhard and Edward Witten. So the motivation for this work is to have some kind of a deeper understanding of loop momenta as well as double copy on the string wall sheet. So if we just look at the string wall sheet, so here's a pictorial cartoon. There are some modes that propagate on this wall sheet. They can go in both directions, and they're also all scrambled up as we go up in time. So our time goes up here in this picture. And now what we would like to have is some kind of a splitting of these modes on the wall sheet, on the string, that go into the left directions, the right directions, and perhaps also some zero modes that entangle the two. So if you come from a scattering amplitudes perspective, you might think of the left movers as carrying some kind of color degrees of freedom, then the right movers carrying the kinematics degrees of freedom. And there will be also some zero modes which tell you how to put that information together into a single amplitude. So of course, that's something which is very easy to do on a single wall sheet. But now we can ask a question, how to pull this off also at the level of the S matrix when we have interactions. And of course, that's something that on the one hand has been done by Kawai, Level, and Tai in the 80s, who showed that at tree level, you have this factorization into left and right movers, which we know nowadays as the KLT formula. And there's also the work of Doker and Fong on something that they call chiral splitting also in the 80s, who generalized this kind of picture to higher loops, also splitting things into left, right movers, and the zero modes. So in this talk, what we would like to give you is a physical interpretation of this holomorphic factorization using the eponymous sandwich model. So the reason why it's called a sandwich is that there will be some Riemann surfaces which are sandwiched together into a bigger free manifold. And there will be some fields living in the bulk, and there will be some fields living on the boundary of this manifold, which will be responsible respectively for the left, right movers, and the stuff in between. Okay, and I have to say that that's something that ultimately won't lead to a drastically new formula, but it will give us some new way of thinking about this holomorphic factorization. And I should say straight away that any suggestions that you might have for further applications of this model are most welcome, and that's the main reason why I'm giving this talk here today. Very good. So before we start, let's have a little insight from condensed matter theory. Okay, and I promise that's something very extremely basic. I will just remind you about something that we learned in the undergrad classes, which is the Hall effect. Okay, so let's consider a conducting disk, something looking like this, with an inner and outer boundary. So there's some electrons living on it. You can think of it as some metal, like such as gallium arsenide. And then we apply a magnetic field to it, B, which will go upwards through the disk. Okay, so then looking sort of top down on it, what is going to happen is that these electrons here will feel the magnetic field, and they will go in circles as usual. Okay, so they will go in the circles in the anti-clockwise direction. Now we can think about what happens to the electrons which live close to the boundary. Okay, so if there's some electron living here, then it wants to move clockwise like that, but then it encounters the boundary. So it will bounce back and go in clockwise direction again and again and again. And ultimately, there will be a chain of modes propagating in one direction on the boundary of this disk. Similarly, you can repeat the same thought experiment close to the other boundary. And once again, there will be a mode that goes along the boundary, but now in the opposite direction. So these modes, which are confined to the boundary, are called the edge modes, and they come with both chiralities. So we had one chirality going in this direction, and one chirality going in that direction. And that's something that has been known since the 80s, and there's a level of experimental verification to these kind of ideas in condensed matter. So in the low energy limit, this effective theory can be described by Chern-Simons theory. Okay, so the action for Chern-Simons is this kind of standard term, and there will be also some boundary terms which are included because of the presence of boundaries. Okay, so here there will be integral over bulk, which is the disk times time, and the boundary, which are the circles times time. And that term is topological, and all the dynamics, or most of the dynamics, will be encoded in the boundary terms. And that's what I wanted to focus on now. So I will spell out what these details should be here in a second. Okay. So, but before that, let me emphasize that because now in this limit, the theory in the bulk is purely topological, it means that the exact width of the disk doesn't matter. Okay, so we had something like that. That's the space-time picture. There's modes moving on one boundary, and there's modes moving in the other direction on the other boundary. But now the width doesn't matter, so we might think of it as shrinking the width to 0, or being like sort of far away from it. And what's going to happen in this limit when we shrink it, then everything looks exactly like a string wall sheet, with left and right movers being almost on top of each other. So going the opposite way, from the wall sheet to this picture, it gives us some kind of a way of understanding how to split left and right movers to be separate. Okay, and of course there could be some topological things happening in the bulk, and that's what's going to connect them. Very good. So now you can ask yourself a question, and that's a question that has been asked. Could this lead to some kind of a new theory of topological, or so-called topological membranes with Chern-Simons world volume? So that's a question that people like Ian and Carl Lipp have been studying in the 80s. So the picture would look something like this, that there would be some kind of membranes of this type interacting. Unfortunately, this kind of theory would suffer from a lot of inconsistencies, or would be at least very difficult to calculate. But what we're going to do is, instead of pursuing this question, we'll just make it a motivation for the following model. Okay. So the way I want you to think about it is that now we have these wall sheets, and there's the outer wall sheet and the inner wall sheet. So on each of them, we have some kind of a CFD. So let's think about what happens when we take one of the wall sheets and using the usual map to Riemann surfaces, we'll deform it to a Riemann surface with vertex operators on it. And the other wall sheet will deform to another Riemann surface with vertex operators. Okay? And that will lead us to the following picture. So, so just to be clear, I'm just considering specific configurations in which there's the same, both wall sheets have the same number of incoming states, outgoing states, and the same genus. So this will give us a motivation for the following model. So it's not a theory, it's just a model. And the model will be on a free manifold which I call M. And it will be given by a product manifold of a genus G Riemann surface, sigma G, times an interval. Okay, so on one end we'll have one Riemann surface, which let me call sigma L. On the other end we'll have Riemann surface sigma R, and there's stuff in the middle. And there will be vertex operators on each, or these punctures on each boundary, which are connected by Wilson lines. So just for simplicity, there's no physical interpretation to that, but for simplicity, let me call this direction time, parameterized by t, and the other direction within the Riemann surface as space with some z and z bar. And what we're going to do is put a Chern-Simons field in the bulk, And there will be these edge modes, which I denote by these symbols on the boundaries. So from now on, you can forget about what I was saying before, and then let's study this model. Okay. So first of all, let me discuss all the fields that are in the game. We have the Chern-Simons field A, which can be split into, so it's a one form living on the free manifold, whose target space will be whose gauge group will be the target space. So in this case, I will just take it as a d-dimensional Minkowski space. So let me notice straight away that that's of course, a non-compact gauge group, so that will have some bearing of what you might expect from your Chern-Simons theory. So this A now has mu indices, which are the space the Lorentz indices, and it splits into a dz form, dz bar form, and dt form. Similarly, I will have the left chiral field, some x left mu, which is now a zero form defined on one of these surfaces, again valued in the target space, and similarly for the right field, which lives on the other Riemann surface. Okay, these are the fields, and now we can talk about the action. So the action is as follows. First of all, we'll have the Chern-Simons term. Okay, so everything is now, our gauge group is abelian, so it's enough to just put the abelian Chern-Simons term, which is ADA. And there will be coupling to Wilson lines, which are simply some external data, which could be some external momenta P dotted with the gauge field. Okay, and there's some coupling constant up front. So let me give you some quick comments about this action. First of all, the coupling constant is not quantized. This K up front is not quantized as a consequence of the fact that our gauge group was just some copies of R, which is a abelian non-compact group. So K does not have to be an integer. Then in this action and in the what I'm going to say later on, I'm using shorthand notation in which, for example, here I omit all the obvious contractions of the Lorentz indices as well as all the obvious edges. We will just clean up the notation a little bit. Okay. And finally, in this last term here, where I discussed the coupling to Wilson lines, I assume that there's no braiding of Wilson lines, meaning that they just go straight, like in the picture, they just go straight in this direction, and there's no braiding of one and around the other. And that means that this term here is just going to be a coupling of P with the time, so just the dt component of the gauge field. Okay, very good. So as the next step, let me say the obvious thing is that this action is not well defined in the presence of the boundaries. So if you just vary this action, it's the variation principle is not well defined, and that means that you have to add some counter terms. And these counter terms, another way of thinking about them is that they dictate the dynamics on the boundary. Okay, so if you just do it, you discover the following action on the Riemann surface sigma L, and it has a couple of terms. So there are these terms here, which makes the gauge field, the Chern-Simons field, which now AZ and AZ bar denotes the field confined to the boundary, together with this X left field, which is the edge mode. Okay, so there are these three terms, which are, one thing that you can notice is that in these terms, X left couples chirally to the gauge field. So you can see, for example, from here that it preferentially selects the holomorphic coupling here. You might also wonder about that these terms look oddly sort of that they can be related perhaps by integration by parts, and that would almost be true, but it turns out you have to actually be a bit more careful with integration by parts because of single validness of your field. Okay, the final term here is the kinetic term, so that's just kinetic term for a boson. Okay, and then in the final line we have the obvious coupling to Wilson lines, which is P dot X left coupling. Okay, that's of course not the end. There's also a completely analogous action, which is the action on the other boundary, which is almost the same. Everything is almost the same, except that the field couples with the opposite chirality. So for example, here, instead of coupling to the holomorphic modes, it couples to the anthropomorphic modes. So that's the opposite chirality. And now with these actions, you can check that for example, if you perform a gauge transformation and at the same time you transform the edge modes in this way, that everything is well defined and everyone is happy. So now is the claim, and the claim is that the sandwich model, which is the model that I was describing, computes scattering amplitudes. And what I mean by this is that if we just compute the partition function of this free manifold that we're discussing here, okay? So that means we do a path integral over the gauge field mod the gauge redundancy, path integral over the edge mode on the left and right boundary, weighted the appropriate action, which is just the sum over the free that we had before, then that computes scattering amplitudes. So let's verify this claim. Okay, so in the first instance, I'm just going to fix the temporal gauge. So that just means that the t component of the gauge field is going to be 0. That turns out to be particularly convenient. In the second step, I will tell you what the equations of motion are in the bulk. So the first equation of motion is that the field strength couples to the external momenta. So that's not surprising. That's just a Gauss constraint. And the second term is also not surprising. It tells you that the variation in time of our gauge fields is 0, which is just a consequence of the fact that the theory is topologically in the bulk. So we can sort of slide things around. So we can slide the surfaces back and forth. Okay, we can also talk about the equations of motion on the boundary, and if you just do the variation of the above action, you will find that both the AZ component of the gauge field is related to this combination on the left surface, and AZ bar is related to the other combination on the other surface. Now we know that since everything is topological, we can slide surfaces around, and in particular we can identify the left and right surface like so, and now we just evaluate the on-shell action. Okay, so I'm just going to sum over these three actions and evaluate everything on shell. Just on the support of equations of motion and the fact that we use this gauge, it's very easy to see that the Chern-Simons action is exactly 0, which is not surprising because everything is topological. And now what remains is to evaluate the other two pieces of the action on the support of these equations of motion. So now we have everything. So AZ and AZ bar will be completely determined in terms of x left and x right. So that's all that remains. And if you just clean it up, it turns out that it organizes itself into these two pieces. First of all, the x left and x right are always added up. So they're always appear together, here, here, and here. And if you call the composite fields just the sum of them x, then that's just a kinetic for x, and that's just a coupling to X operators as usual in string theory. So we would conclude that the partition function computes a genus G contribution to the scattering amplitude of tachyons. These are tachyon vertex operators, where now we can identify this K, the coupling constant up front, with 2 over alpha prime from string theory. And let me remind you that everything here was done at fixed moduli of both positions of the punctures and also moduli of the Riemann surface. Very good. So at this stage, let's exploit a different point of view on the same problem. And the different point of view, it would be kind of boring if that was the end of the story. Okay, we just found that it's a different way of representing scattering amplitudes, but now we can exploit the fact that everything factorizes into left and right. And what we're going to do is define a left wave function, which is just going to be we're going to slice our sandwich model into two separate pieces. And the left piece will define some kind of wave function coming from the left, and the right piece will define a wave function coming from the right. And of course, this is designed in such a way that if you put these two things together, we would recover the original sandwich. Okay, so both of these wave functions are functionals of the gauge field, which remains to be integrated over. Okay, so that gives us an alternative representation of the amplitude. So now we can represent the partition function z, as is usual with in topological field theories, as a bracket of two wave functions, which are the objects from here. Okay, so once we have these wave functions, what it means to take the bracket is to integrate over the remaining phase space in the middle, which are the gauge fields modulo fixing. Very good. So now you might wonder, well, how do we find these wave functions? And that's something that is was studied and is known as the geometric quantization of Chern-Simons theory. So that dates back to the work of Axelrod, Della Pietra, and Witten in the 90s. So let me just, I didn't want to get much into, because of the time constraints, I didn't want to get much into the specifics. I'm just going to show you some of the equations that come out of this quantization. The first one is sort of the obvious one, which is the Schrödinger equation, which tells us that the time derivative of our wave function is 0. And that's because the Hamiltonian for our system is 0. And that just tells us that we can slide things around back and forth. So again, a quantum version of what we've seen before classically. And another constraint is this Gauss constraint, which there's some operator acting on the wave function, which once again is a quantum version of the Gauss constraint that we've seen before. There's now another piece of the construction, which is now a choice. So it turns out you have to commit yourself to some choice of polarization for this wave function. And the choice of polarization that I will employ is the so-called holomorphic or Kähler polarization, which amounts to imposing this constraint. So this constraint makes sense because in the Chern-Simons theory, the AZ and AZ bar fields are conjugate to each other, and that's effectively what this equation imposes. Okay. So now, just as a consequence of this last equation, we can solve for this wave function. Okay, so let's focus on this piece. So this was a wave function which used to be a functional of both the AZ and AZ bar components. And now, on the support of this constraint, there will be this overall piece which just solves this equation. Okay, so exponential of integral of AZ bar components of the Chern-Simons field. And now there is a factorization that there is a piece that comes out which is fully depends only on AZ bar, but not on AZ. And similarly, that was the left wave function. And similarly, you can repeat the same exercise for the right wave function, just derive all the equations. And what you will find is that also there's this overall piece coming up front times a factorization on of a wave function that only depends on AZ. So what I wanted to stress is that these two pieces are purely holomorphic and anti-holomorphic respectively. Okay, so now we can write our bracket of our two wave functions in the following way. So we have once again the path integral over the gauge field. Then there will be these two pieces that are just products of these two. Okay, so there's this piece up front, and usually this is actually related to something that is called Kähler potential of our Riemann surface. So that's what goes up front. And then there will be a factorization of holomorphic and anti-holomorphic modes into these two wave functions. And that's hopefully, if you just carry on with that story, you would discover that that something completely expected happens is that this piece of the wave function is just the integral over the remaining left modes with the left action that we've seen before, and now subtracting the term that goes up front, half of that term. And then the other piece of the wave function will be exactly analogous term for the right edge modes. So there will be this piece of the action with a subtraction. Okay, so everything is now well defined. So to complete the quantization procedure of this first homology, we need to expand our gauge field. Okay, so that's something that's in a sense, we've seen a version of that in the previous talk, that once I have a gauge field, I can expand it in a basis, and there will be a basis of abelian differentials. I will remind you in a second how they're defined, and there will be abelian differentials of the third kind and abelian differentials of the first kind. Okay, and possibly some pure gauge terms. So now, if you just plug this into equations of motion, you will find that these terms here, which are the ones measuring how the gauge field changes when it goes around punctures, these are actually completely fixed by equations of motion. Okay, so this is just external data. But it turns out that equations of motion would not tell you what these coefficients are. Okay, so this will be some unfixed degrees of freedom, and suggestively foreshadowing what they will actually become, I will call them L. So there will be one L for each genus valued, and that's a Lorentz vector, and there will be also L bar for the antiholomorphic version. Similarly, so here at the end, what I will do is fix the remaining gauge freedom by fixing this eta going to 0, which will allow us actually to talk about x left and x right as being purely holomorphic and antiholomorphic, respectively. So just to emphasize what these new variables here are, I can just invert this equation, and I will find that this loop momentum L, what it measures is the value of the gauge field as it goes around this dz component of the gauge field as it goes around the cycle, say a cycle. And L bar similarly will be a component of the gauge field as it goes, dz bar component of the gauge field as it goes around the same cycle. Okay. So how am I doing on time?
So you've got about another 2 or 3 minutes.
Oh, perfect. It will take longer than that. So here's a quick reminder about the abelian differentials. So we use these two abelian differentials. That was the one of the first kind entering here. That's the one that if you choose to measure something along a handle, so some cycle aj, if you put this abelian differential, it will give you 1 exactly when I and j are equal and 0 otherwise. And also we use these types of abelian differentials here, omega, which depended on 2 punctures. And these are abelian differentials of the third kind, so they have singularity exactly at 2 points on a Riemann surface, in such a way that if you take a residue around some point j, it's equal to +1 if j was the puncture r, and -1 if it was the puncture I. Okay, and here and in the upstairs, I used a reference point, ZR, some random point on a Riemann surface, which enters here. So you might be worried, but actually the dependence on that reference point cancels out by momentum conservation. Very good. So now, similarly, what we can do is we can keep going and expand now our edge modes similarly in a basis. Okay. First of all, this one is purely holomorphic. This one is purely antiholomorphic. And once again, we have some basis of third kind differentials and first kind differentials. And as before, these pieces are entirely fixed by equations of motion. And then you might be slightly worried about the other pieces because equations of motion do not fix it. However, imposing that the composite field x left plus x right is single valued on your Riemann surface implies that this coefficient here up front, Q, has a specific form. And that specific form only depends on the moduli of the surface, abelian differentials, and the external data. So actually, these edge modes are completely fixed. So just to summarize what we found so far is that we have our action in terms of A fields, which depend on the external data as well as unfixed variables. And also they depend on the X fields, which is now completely fixed in terms of external data. So what remains is when we want to evaluate the path integral, is that what remains is only integral over these zero modes, what I called L and L bar. And now we'll have this exponential of the Kähler potential as well as the wave functions, which one of them depends only on one type of loop momentum and the other one on the other. Okay, so now everything is expressed in terms of these L's. So the only thing left to do is actually to evaluate integrals over abelian differentials. Okay, so if we plug these things into the action, we'll only have some integrals over these kind of objects. And these are fully known. You can work out using Riemann bilinear relations. If you're careful enough, you can work them all out. And now they're given exactly in terms of some data that we expect to know, some integrals over first and third kind differentials on the Riemann surface. Okay, so after you just plug this into the action, into the above action, this gives us the final answer. Okay, so the final answer is as follows. Our path integral, which remember is the different representation of a scattering amplitude at fixed moduli, will be given by this double integral over L and L bar modes. And then, as expected, the rest of the integral will factorize into a mod square of something which is purely holomorphic. So that will be given by an exponential of these p dot p terms. Okay, there will be terms that involve p dot real value of the loop momentum, and there will be terms which depend on L and L bar. So here's a couple of comments. So let me notice that in this last term here, L times L bar, which can be alternatively written as real times imaginary, the only place where imaginary part of the loop momenta actually appears in this action is here, and it's purely Gaussian. So it completely decouples from all the rest. So that means that the imaginary parts of the loop momenta decouple, and after we just integrate them out, it's just Gaussian. We obtain the chiral splitting of Docker and Funk in exactly the way that they wrote it in their papers. And of course, additionally, integrating out also the real parts of the loop momenta will recover the usual non-holomorphically factorized representation of scattering amplitudes. So let's very briefly, I'm well over time, but I'm going to scroll through the slides to recap what we've done in this talk. So we started with thinking about how to split our modes into left and right movers and zero modes on the level of the S matrix. And we're motivated by this Hall effect in condensed matter theory, in which there are some boundary modes which decouple from the topological theory in the bulk. And then we ask that motivated introduction of the following model, which is a sandwich of two Riemann surfaces with a Chern-Simons field in the middle. We introduce the action, and we claim that the partition function of this model computes as tachyon scattering amplitudes. Okay, then we verify this claim by showing that everything just becomes a free complex scalar coupled to vertex operators. And that motivated us to talk in a different way about the same problem as a bracket of two wave functions, one carrying left degrees of freedom, the other carrying the right degrees of freedom, such that sandwiching them together gives us the final answer. And what we found after some algebra is that the final answer is given by this holomorphic factorization of the two wave functions with these loop momenta in the holomorphic and anti-holomorphic directions. So possible extensions would include, let me just very briefly say that, for example, coupling to gravity, which promote these moduli to dynamical degrees of freedom. Then you can ask about superstrings, which would either amount to adding some fermions on the wall sheet or the free manifold or considering super Riemann surfaces. Lastly, or another thing that you can think about is studying different types of vertex operators, and this would of course correspond to inserting various different representations on the endpoints of the Wilson lines. And finally, perhaps more ambitiously, you can think about the generalization of the sandwich model, which would reproduce something like an ambitwister or sectorized string. So with that, let me thank you.
Thank you very much. Very, very nice talk. Again, if people have questions, please raise your hand. Ricardo, you have a talk. Ricardo, you have a question.
Hi. Well, thank you for the very nice talk. Let me just first ask a very naive question. So I guess the topology of the two sides of the sandwich must be constrained to have, say, the same genus. Is that completely obvious in the model?
Yes. So as I said at the beginning, what we consider is this free manifold M, which is genus G Riemann surface times time.
Okay.
Interval.
Yeah, but I guess one could imagine. Yeah, one could imagine. However, I mean, is there a way of imagining this like a more complicated thing?
So you might be referring to what, at least partially, I took as a motivation, which was this theory of Kogan and Carlip, who imagined sort of, making it a theory. Unfortunately, that suffers from many problems, and one of them is a thing that you might be referring to now, which is that if you actually wanted to make it a consistent theory, you would have to sum over all topologies, or geometries in all topologies, and that doesn't necessarily imply that everything is the same, like both world sheets would have the same genus, or there could be some crazy free manifolds that you would have. Most likely doesn't lead to a consistent theory. And that's only one of the problems.
So another question was, you said at some point that you fixed some exact parts of AZ and AZ bar.
Yeah. To zero.
Yeah. So let me just look at it again. Yeah. And that creates a splitting into a chiral, anti-chiral factors.
Exactly. So one way of thinking about it is that that's what allows you to separate the x left from x right. So of course by gauge transformation.
I see. Can you imagine doing something else? Because say in the ambitwister string you have chiral, and of course somehow it's not a string theory, and it's not clear how one could think about it.
Yeah, sure. So let me comment on that. So when we consider just the pure Chern-Simons theory, even by the arguments that I was trying to motivate from the quantum Hall effect, is that you always see opposite chiralities on the boundaries. They just depend on the orientation of the boundary. You would always see holomorphic modes on one boundary and anti-holomorphic modes on the boundary with the other orientation. So there's no way of avoiding that. If you wanted to have something like ambitwister string, you would have to be slightly more clever to have something like or even sectorized string, to have something like left movers and left movers, or maybe left movers and some delta functions or something like this. So whatever it is, it cannot be pure transimus theory, of course.
Okay, thanks.
Henrik, you had a question?
All right. Thanks for the nice talk, Sebastian. So I had maybe a trivial question. So your Chern-Simons coupling was 1/alpha prime, I guess?
Yeah.
Which it makes it dimensionful. Is that correct? Or that
yeah.
seems a bit strange. So why is it dimensional? I would naively assume it should be dimensionless.
If you no, K should be dimensional. You can just do dimensional analysis of on the action, and you will find that yeah, K has to have dimensions.
Mm-hmm.
Is that not what you expected?
Well, I was expecting I guess it's a 3D theory, or am I confused? Then the coupling should be dimensionless for Chern-Simons, but.
Oh, but usually people wouldn't write something like h bar in here, so K would have dimensions of h bar or something to that effect, and that translates to alpha prime, 1/alpha prime.
All right. Okay. Maybe it's not too important to discuss. Another question I had was, can you use the sandwich model to describe some simple model that we know well, like the bi-adjoint scalar theory, or is that it's not closely related? Or
yeah, so if we wanted to describe bi-adjoint, well, something that to lead to in the low energy limit would give us bi-adjoint scalar, then right. What we have to do is to attach to the endpoints of these lines some current algebra that we know that is necessarily something that gives us bi-adjoint theory in the low energy limit. The goal would be that once you do this, then the left wave function would be something like sum over Park Taylors, and likewise for the right wave function addressed with the corresponding color factors.
Okay, thanks.
Nima.
Hey, I just have a quick question. I think you may have answered it already, but can you consider like a more general cobordism between two different manifolds on the left and the right?
Presumably you can, yes.
And what do you?
We haven't done
how you might interpret that? Do you have a picture for how you might interpret that?
No. So as I said, the ones that we consider specifically is this product manifold, and I'm just saying that in general you can imagine that's in the realm of things that people would do in Chern-Simons theory, that you would put together glue together two different free manifolds, but I'm not sure what the interpretation of that would be in the string theoretic terms.
But nothing goes wrong, right? I mean, you can define this path integral and
you can certainly, yeah, you can, yeah, absolutely, you can certainly define things, yes.
Thanks.
Zvi?
Yeah, hi, thanks. That was a very nice talk. Maybe you can comment on whether you can use this to figure out prescriptions at loop level in field theory for doing the double copy. So good choices of loop momenta that make it possible to do double copy straightforwardly.
Right. So I'm not sure about the word straightforwardly here, but I can comment a bit on the choice of loop momenta. One aspect is that at some point we made the choice here, and the choice was for the choice of polarizations of these wave functions. And that effectively is what translated to the fact that we have this L and L bar variables. And of course, you might wonder what happens if you make some other choices. So this is just a choice that you can make. And there's various choices that people consider. One of them would be real polarization, what is called real polarization, which most likely gives you a different type of loop momentum, and what that is most likely the one given to us by Docker and Fong. And another, so that there's some room for exploration there. And another aspect is that here we've done everything at finite alpha prime in theory. So you might also wonder what happens to all that theory once you start degenerating the Riemann surfaces on the left and right into something that looks like string theory limit. And that sounds very interesting, but we haven't explored it yet.
But it's certainly something you can explore and hopefully learn something from, I assume.
Oh yeah, absolutely. So one goal would be to see what happens to these various prescriptions as you take the field limit, and what happens to this loop momentum.
That's very interesting. Okay, thank you.
Thank you.
So Atul, you had a question again.
Thanks. Great talk. So the data of your choice of target space R1, D minus 1 sort of entered in that very curious place as your gauge group. So I had two questions. One, basically, if you can replace it with some other group manifold, do you get amplitudes in some other group manifold type background? And the other, how do you hope to put an ambiguous space as a target space, because it doesn't look like a group manifold?
Okay, so the second question is easier to answer because I just don't know how to pull off the ambiguous model in this formulation.
Right.
You can certainly, so that's left as an open question. You can certainly try to put different group manifolds in here, and that's actually what happens in the usual condensed matter theory applications. You would put SU2 or something like this. And but then I'm not sure. What you would have to show is that that gives you some kind of WZW model with the target space being your gauge group. Maybe you can hope to do something with ADS 3x3 like David has done recently, but we haven't explored any of these possibilities. Well, one thing would be that the one curious thing would be now that the coupling would be quantized.
Right, it's not quantized here.
It's not. I'm not sure what that.
Does it have an interpretation then?
I'm not sure.
Cool.
Radu?
Thanks, Sebastian, for a nice talk. I have a question which is somewhat related to NEMAs. So since you picked genus G Riemann surfaces on the left and on the right, this sounds more like a closed string type model. Do you know what happens if you were to pick some open Riemann surface on the left and on the right?
Yeah, one curious feature is that actually that's not possible, and the reason for that is that we deal with a free manifold, and that free manifold had a boundary. So of course, a boundary of that boundary has to be 0. So that means that you cannot put an open Riemann surface in here. But there is something that you can try instead, and that's something that has been explored in the 90s by people like Hojava, who put instead similar type of Chern-Simons models on orbifolds. And it turns out that if you do it on orbifolds, you can put something with a boundary, and the hope would be that that would be something that, that's something that smells like open string theory. So if there was any direction towards open string, that's what I would consider.
Yeah, so the more general question would have been if there is an open string version of your model, in perhaps in the same sense of open-closed duality or something like that.
Yeah, that would necessarily, at least I think, would have to necessarily involve these kind of orbifold constructions for the free manifold.
Okay, thanks.
In fact, you could just ask whether, as a special case of the question you asked before, whether you can just put an end-of-the-world brain, let's say, to replace the guy on the right. So now you just have the data of a single Riemann surface, right? Is that what you had in mind, Sebastian?
Not quite. What I would mean is that you would, well, that's perhaps a possibility. What I would mean is that you would consider reflection of your manifold with a fixed point, which is.
Well, that's the same thing.
Yeah, that's the same.
Oh, okay.
Yeah. You don't have to use the orbifold language. You're just ending the free space on that reflection plane. Yeah. Okay.
Well, either if you don't like. They're the same, right?
Exactly the same. Exactly.
Though in principle, if you make your three space singular in some sense, you might invent a boundary of a boundary, which isn't necessarily 0.
Yeah, I think that's effectively what we're talking about. That's the mechanism I would